for this session. So just settle down and get ready for the session. So good morning again. Welcome back for the second day of the MGA conference. Can you show my slides? Just to give some introduction, I'll quickly go through that, please. Thank you. So this is the session on innovation in GNSS application. It's a session that's chosen with the title that we want to showcase the innovation in the usage of GNSS technology. So it could come in two parts. One part is about the provider part, how to provide innovative applications, as well as it can come in the part of the user. How do you use the technology in the innovative way? Yeah. So we have a whole list of presenters today. If we can go to before that, let me introduce myself. I'm Victor Khoo. I'm the Director for Survey and Geomatics from the Singapore Land Authority. I'll be your moderator today. I have a very simple agenda. There are 7 presenters in the list. I'm not sure whether all of them are here today, but I have a couple of them here already submitted the slides. Each presenter have a very short presenting time, and hopefully at the end we have some time for Q&A. And I would like to really keep this session to 1 hour. Yeah. So without further delay, I want to know if Mr. Akira Lihoshi is around. If not, I'll give the floor to Asari-san from Japan Space System, to kickstart the presentation of today.
Yeah.
Yep, the
Thank
floor
you.
is yours.
Please stand up my presentation.
Yeah.
Asari's presentation, please. Thank you. Thank you very much. I'm Koki Asari, General Manager for GNSS Application Frontier Division of Japan Space Systems. This is incorporated foundation of Japan. So I talk about GNSS innovation in the standards. Yes. We have standards on GNSS, but standard have 3 kind of standard. So first one is de jure standard. De jure standard means based on international treaty. For example, in this case, WTO agreement. WTO is World Trade Organization. This is trade matters. So international cooperation, in international cooperation, the trade is very important for powerful economy. The examples are ISO, IC, ITU, and so on, and ICAO in the aviation, the maritime, the IOC. The second item is forum standard. Maybe you use these standards very much based on civilian forums. For example, RTCA, RTCM, and NMEA. Maybe you use very much for product makers. And the third item is de facto standards. This is based on dominative market share. For example, Android and iPhone GNSS APIs. Oh, sorry. I'm sorry. Yes, in the standard, we have 3 kind: de jure standard, forum standard, de facto standards, and so on. So, at first, I'd like to introduce the new standard of maritime navigation. this is IEC standard. Recent topic, 2023, Indian Naval Sea maritime receivers is established last year. And right now, soon, SBUS, maritime SBUS receiver standard established, and product maker has a powerful chance of in the market. And QGSS receivers next items right now in proposal. So recent topics in ISO, a new working group is established 2022. So this is a downstream space service working group in the Committee of Space Systems and Operations. And this working group has 4 pillars, PNT-GNSS and remote sensing and the communication using LEO satellites and space weather. So it covers land applications, maritime applications, aviation applications,
To change
and
your
so
slide.
on. Yes.
You didn't change your slide.
So a new,
Slide.
difficult, I'm sorry. This slide shows new working group of ISO. It's dedicated to downstream space services and space-based applications for land, maritime, and aviation. So one example of a new proposal is 25082 proposed by France. This is related to the ITS intelligent transportation system, including autonomous mobilities. This standard specifies definition of system engineering procedures and establishment assessment of performances. So France proposed other parts, 2 parts, and the basic performance of terminals, and part 3 is assessment of security performances. Part 4 test scenario is specifies. We are focusing and review this standard. So this working group has a collaboration categorography, the other committee of ISO and IEC and space organizations, the United Nations, and other forum standards, including 3GPP and FIG and IEEE and IANS. But a decision is made and national voting. National voting make a decision of rule making of GNSS. So in Asia Pacific countries, less members right now. So in Europe has many members. So it means much number of voting. So we need a member of Asia Pacific. Please join this committee. And through your country's standardization body, maybe country have a standardization body. For example, in the Japan cases, this association. In the Australia have a standard Australia. Each country has a standard body. You can join, and please let's take part in these committees from Asia Pacific nations. Thank you.
Thank you. Thank you, Mr. Asari, for keeping to the time. Yeah, thank you very much. I have to keep the question answer to the end. I think maybe if you have any questions, you can approach Mr. Asari directly. Yeah. So I'll move on to the next speaker because there are 7 speakers here. I need to really move with time. I understand that Mr. Lihoshi is online. Can we bring Mr. Lihoshi up? Is that correct? Can you do that? Because I just saw him online just now. Akira Lihoshi from Pacific Consultant. Is he online to present? Yeah, can you bring him up for the presentation? Okay, if you need some time, maybe we'll just wait for the next presentation. I'll give the floor to Ms. Dr. Parayok. Is Dr. Parayok here? Okay, if not, I'll give the floor to Dr. Tadashi Sasakawa from the Kokusai Kyogo. Yeah. I'll give the floor to you.
Good morning, everyone. So I'm Tadashi Sasagawa from Kokusai Kogyo in Japan. So Kokusai Kogyo is one of the biggest survey company in the world. We have 2,000 employees. So so today I will introduce our experiences as a pilot experiment of Madoka PPP for base point installation. So subtitle is Madoka PPP Utilization Technical Guideline Development Project. So at first, I have to say the project was adapted for the public competition. So application demonstration using Michibiki, so QGSS, organized by a Cabinet Office and QGSS Services Inc. Okay. So you're so very specialist for the GNSS. You have known well, so the differences relative surveying or so direct surveying. That means if you have some course or any existing control point, it's easily to measure so the distance. So using relative positioning, but if you don't have any such kind of control points, so like remote island, so too far from land, so we have to apply so SPP or PPP. So you can understand is the PPP is the most effective. So how effective? So we have to verify this situation. So we are now targeting for the official surveying for remote island, where not access to any other course or control point. So in this case, it's, we operated PPP in Philippines. So Philippines Geographic Information Authority, its name is NAMURIA. They have regulation to measure such kind of remote island with SPP. In this case, they are now measuring for 8 hours. So only stand-alone GPS. So it's you can imagine. So if you are going to a remote island, it's for 8 hours. It's a very so severe work to carry battery, water, or so no internet. So Madoka PPP is available to augmentation data from QZSS directly and free. It's important. So in this pilot system, we comparing RTX by Trimple. It's also the commercial so PPP. So, but in this case, is commercial. That means not free. So finally, so how to use Madoka PPP to apply official surveying in remote island. So we have to make a technical guideline. So how long measure? So how to inspect? So the if it is correct or not. So in this case is we criteria so have standard deviation at 5 centimeter. So that means cycle error 95 is 10 centimeter. So and vertically accuracy, sorry, I'm sorry. So so vertical accuracy is standard deviation 10 centimeter and CE 95 20 centimeter. Then so how to realize such kind of criteria of accuracy. So at first we did the verification experiment study in Japan. So sorry. So two cases of verification. So one is to verify the suitability. So to measure for a long time. So and the second case is to automatically measurement. So using with baseline field of Geospatial Information Authority, GSI, Japan. So you can see that it's a flow. It's we are using a splitter in the simultaneously. Its signal is divided to Madoka and RTX and so original data so capturing. So this is the result of the 72 hours of observation. So blue is the vertical side of SPP. The orange is also the horizontal side of SPP. So yellow is Madoka PPP. So one span is 8 hours. Then totally 72 hours. So so you can understand very easily to how so effective. So in cases 8 hours, so that is a regulation of NAMRIA to measure so coordinates by SPP. So we can reduce the time, so measure time to from 8 hours to 30 minutes. So it's a convergence time. So also the accuracy is reducing 2 meter to 10 centimeter. It's very easily understand. So second case is to using a baseline field observation. So the
Yeah, 1 minute.
1 minute. Okay. So I'm sorry. So we did it. So evaluate all of data. Then finally I reached to the result. So it's this shows its vertical axis is number of over accuracy. So it's reducing according to the time series. Finally, so 1008 second. So measure observation time is the best fit for realize criteria. So accuracy 10 centimeter. So under vertical accuracy, it's 20 centimeter is also the 108 hundredth second. So then, based on this result, we did the guideline. So 100 epoch from 1700 to 1800. It's a one set. Then evaluation. That's an inspection of using two sets. And the differences of the sets between 100 millimeter, 10 centimeter. It's good. This shows its final result of the verification and the inspection of the data. So look at this one. It's a 10 centimeter less. It's this one. The 20 centimeter less. It's almost the data is within this guideline inspection.
Thank you.
Yeah.
Thank you, Mr.
Sorry.
Sasakawa. Thank you.
So
Thank you for
finally-
sharing with us
Okay.
your work
Sorry.
in Maduka PPP.
PPP.
I have to give the floor to another speakers online.
Online. Okay. Sorry.
Mr. Lihoshi-san, is he online? Can we get him up and present? Thank you. Thank you very much.
Okay, I share my presentation.
Thank you. Yes, Mr. Lihoshi, the floor is yours.
Okay, just a moment. You can see my presentation?
Yes, we can see your presentation. Go ahead. You have
Okay.
about 9 minutes.
Oh, yeah, okay. Good morning, Sawadee Krap, everyone. I'm Akira Ihoshi from Pacific Consultant Japan, and I'm happy to share my presentation with you today. The focus of this presentation stems from a project committed by the Ministry of Internal Affairs and Communications in Japan. Today, I'll be discussing our findings regarding road surface measurement lane by lane and flooded area altitude measurement in this feasibility study. Let's dive into the contents of this presentation. Okay. In essence, our aim was to kickstart a new business utilizing Multi-GNSS through this feasibility study. We had 3 services utilizing Multi-GNSS in this feasibility study. First is location detection service for stolen motorcycle. Second is a road information service by then with road surface measurement of vehicle. Third is prediction service for road profile and flooding hazard areas. The location detection service for stolen motorcycles involves cars equipped with a Mitsubishi receiver detecting a Bluetooth ID of a stolen motorcycle, accurating users to accurately identify its location. The road information service collects and provides road surface information by them. The prediction service is using Mitsubishi to provide attitude information of flooded areas. Despite similarity to Apple's AirTag, the principle of stolen vehicle location detection using Mitsubishi did not improve position accuracy. Moving on to the result of the road information service by then, we confirmed that the position of the Mitsubishi receiver can capture data by then, but it's not possible due to some accuracy issues in high-rise building areas. Driving on each lane of a 4-lane road with a road condition measurement vehicle, revealed areas with a poor road surface condition highlighted in red. Next, I'd like to explain Mitsubishi receiver. We utilize the Kohaku 10 Plus receiver showcased on the core company website. Mitsubishi receiver's horizontal precision standard deviation was approximately 2 or 3 centimeters upon actual precision checks. And attitude measurement at triangulation point in Japan showed an error of around 10 centimeters. And altitude difference error was approximately 2 or 3 centimeters. Next, let's dive into the detail of lane identification. As seen in the trajectory when driving on 7 lanes in Manila, positioning becomes impossible under obstruction. However, we are able to interpolate using the dead reckoning method. Mathematical lane identification involved calculating straight line equation for each lane and the intervals between them, representing the actual lane spacing. Now let's discuss the positioning accuracy when driving the skyscraper district. Position accuracy suffers due to obstructions and multipath effects. This close-up reveals the worst spot. Altitude measurement of flooded area depict lower altitude was indicated by darker blue. Altitude measurement in the flooded area of Jakarta indicate lower altitude in the residential area compared to the main road. Residential area of main road. In summary, The road information service by lane with road surface measurement vehicle utilizing Mitsubishi allowed us to identify lanes on the highway. However, in the presence of obstruction in the sky and in skyscraper district, accurate in lane identification was insufficient. Next, in the prediction service for road profile and flooding hazard areas utilizing Mitsubishi, we are able to measure height difference and visually presence variations in road surface elevation. We anticipate being able to introduce novel service leveraging Mitsubishi, such as utilizing road elevation maps to analyze water flow pattern and develop optimal wastewater treatment strategies. Thank you for your attention.
Thank you, Mr. Lihoshi, very much for keeping to the time. Can you stay online for a short while we try to continue the presentation? I think the Q&A will come back to you later.
Okay.
I would like to check for my speakers. I think Dr. Prayok, is Dr. Prayok here? Okay, I don't see him here. Colonel Sompok, are you here or online? Can I check? Yeah. Mr. Virendra, are you online also? And also, last but not least, Mr. Jeremy.
Yes, I'm online.
Jeremy, you're online? Okay, perhaps you go ahead with your presentation first while we try to locate other speakers. Yeah, so
okay.
Please help with Jeremy's slides first. Thank you, Jeremy. Yeah. So
thank you, Dr.
The floor
Ko.
is yours. You have about 9 to 10 minutes.
Okay, I'll share my screen.
I think we have a bit more time now when we have some speakers are not turning up. Go ahead.
Are you able to see my screen properly?
Not yet. Yes, loading now. Yes, we can see your screen.
Okay, thank you, Dr. Ku. Thank you, everyone. And Sawadee Kap. Today, I'd just like to talk mainly about the post-processing software for INS and GNSS. Very briefly, SBG Systems is a French company. We have several offices, including one in Singapore, where I am located. We started from the IMU, not really from the GNSS at start, but by focusing with the IMU and the fusion with GNSS to develop INS. After releasing many hardware, we are also now developing a high capacity and expertise in a GNSS processing, particularly through post-processing. So Kinesia is one of our solutions that we dedicate to a surveyor, but also to any company that wants to do a dynamic testing or ground truth reference. As we have seen in other presentation, we also always have a few difficulties with the real time. When the GNSS signal is complicated, it could be mitigated, of course, with IMU, but sometimes it's not enough, and this is why PPK software is a must-have. why is PPK in particular interesting? Well, in case of IMU, of course, is the capabilities to improve the data and to maintain a high accuracy. In case of GNSS outage. Why? Because in real time, you are sometimes limited by the CPU of your embedded product, but also because in real time, you can only have access to the past data that you have. When in post-processing, you can actually have a complete view of your data, meaning you can see the past, but also the future of a point and of your trajectory. And in that case, you can do what we call the forward, backward, and then a merge in order to get the highest accuracy. The other advantage of post-processing is the ability to get rid of real-time communication equipment. If you don't want to have a communication between your rover and your base station, it's possible to directly have access to base station and course network that are around the world. It could be free or paid, of course, but at least you can have a more reference station accessible quickly. In addition to that, of course, you have access to this course station, but post-processing allows to have accurate virtual base station. So playing with multiple base station in order to increase the accuracy. Because, for example, you have long trajectories in case of aerial survey, for example. We can also have access to a free PPP 24 hours after the mission, and this is particularly interesting in case of remote islands, for example, or offshore survey. Something else interesting, of course, is to be able to better control the GNSS signal. In case of inertia, you can, for example, exclude some constellation. You can even exclude some NGOV satellite if you want. So you have access to, of course, more things than in real time to have a better monitoring and better assessment of your data. Something interesting also is to have more data integrity. We have a different approach, whether we can use GNSS only in a post-processing kinematic or with a PPP. We can also use IMU in terms of loose decoupling, tight coupling, and of course additional tight coupling in PPP. A new ability, for example, is now to be able to use, in case you had a real-time communication between your rover and your base station, you can also use this live stream RTCM to directly integrate it in our PPK software. Okay, let's talk a bit more about innovation here. These are previously are very generic, even if we do it well for several years. Another key point of PPP, of course, is to have an accuracy retention of a long baseline. So the RTK is nice, and of course it's very interesting to have a centimetric level of accuracy, but sometimes you cannot reach because you have a long baseline. Or more and more today, you have some very high solar activity, and as you know, for GNSS, it's method of differential, but the ionospheric irregularities are more and more complex. And particularly those coming years, we expect the peak of this solar activity to be around 2025. You have probably already seen as a surveyor that your accuracy close to your base station is already drastically reduced. So before you can really achieve centimetric around 20 kilometers, but sometimes, of course, it depends of the day, of the location, of the time of the survey. It could reduce drastically to these solar activities. What we have done and what we have newly released, it's new algorithms. We call it IonoShield. This is the capacity to mitigate these errors induced by the solar activity. what is interesting is we are getting access, of course, to database available on this solar activity and ionosphere regularities. But instead of taking it locally, we extrapolate the data and we recompute it directly into our software. This gives us the capacity to maintain a very high accuracy, even in long baseline, and also to reduce the convergence time. Just to finish quickly, how it is handled inside the software, it's very very easy. We have directly an interface, and we have set up, of course, some activation threshold. This is depending on the total electron content unit, but of course you can activate it. Sorry, you can activate it as well manually. IonoShield is not magic. Of course, there is always some drawback. We have to be honest. It's a bit more time consuming, and we have, of course, a requirement for high quality satellite signals. So if you are using GNSS purely with no IMU in urban environment, it could be a bit complex to handle. Thank you, everyone, and I'll be ready for question later.
Thank you, Jeremy, for sharing with us a new method. We have already heard from 4 speakers. I'm still looking for the other 3 speakers. I don't know whether they're online or not. Are they? We actually ahead of time. We have another 15 minutes to go, so we can go into the Q&A if I can't find the speakers online. I'll just ask them, if you're online, please identify yourself. Just don't be quiet. So if not, okay. So we have heard from 4 speakers today on the different innovative applications of GNSS. I would like to open the floor for any questions for the speakers, for the 4 speakers. Dr. Sasakawa, please join me. Anyone has any questions for the speakers? So 2 are present here and 2 online. Maybe I would start with Asari-san. I actually want to give the floor to you back again now, because you have some message that you want to share with the participants, some requirement. Yeah, so I'll give the floor back to you for a short while. It's an important work that you are doing, and you are trying to get some participants here.
Project.
We have a bit of time now, so I'll ask Asari-san to say something important.
Yeah, come back again, and I explain today's situation. Can you project my slide? Possible?
Oh, you have to unplug that one. Yes, sir. You have. Yes.
Yes. I'd like to say my message again. So there is a standard on GNSS, 3 kind of standards. First is de jure standard. It is based on the international treaty. For example, WTO, World Trade Organization Agreement. The example is ISO and IEC, and ITU for communication, ICAO for aviation, IMO for maritime, and so on. The second item is forum standards. We use this standard very much. This is based on the civil forums. Example is RTCM and NMEA. And the third type of de facto standard, this is based on the dominate market share. We use very much. For example, Android and iPhone GNSS APIs. So now new working group is established in ISO TC20 SC14 named downstream space service and space-based applications in the covered land applications, maritime applications, and near space applications. This committee is chairman is from United States, and working group convener is from France, Miguel Ortiz from FL University, and I'm a deputy convener. So right now, so member is Asia Pacific member is less. So European countries, many countries take part in this committee, but I'd like to say let's take part in this committee from Asia Pacific nations. Your country have a standardization body, so you can join this committee through the standardization body in your country. Thank you.
Thank you for that. Yeah, I think it's important message, an important work that you are bringing. And for Dr. Sasakawa, I think you have one more slide that you would like to emphasize on. I'll give the floor back to Dr. Sasakawa. Sorry for rushing you just now.
So thank you very much. I'd like to continue to the end of my presentation. So I said it's we made a technical guideline to apply Madoka PPP for remote island surveying, offshore surveying. So according to the guideline, we did the actual remote island surveying in Philippines. So at first, base point, base control point. So Madoka PP. Measurement 30 minutes. Verification for set between sets. So then, we are going to the Manok Island to measure the data. This is Doga. So, radio communication. So on the other hand, we did measuring by same points. So this is the result of the comparing the RTK and Madoka PPP. But this RTK is from the base point. Base point defined Madoka PPP. So it's RTK is using to reduce the time. So it's a very useful combination. And I have to say the how to adjust this.
웨브만 5분만 마우스 저 있잖아요. 그건가?
Can we try to mute the participant online? Okay, Dr. Sasakawa, you
Yes, sorry.
carry on.
So it's hurry up. So, and the important thing is Madoka PPP is on the coordinate system of WGS 84. That means the current coordinates. Then, so we have to convert this coordinate system to national geodetic coordination. So in case of Philippines, so from WGS 84 to PRS 92. Then we are now proposing using a few courses, so long distance for each courses. It's using to adjust WGS 84 to PRS 92. It's using a Helmut transformation. It's one of the easy way to adjusting. So this is a result of the not Philippines, but 4 years ago. We applied this methodology in Indonesia. So in the case of data, red is original, and Helmut transportation, so final result is blue. It's adjusting to the true value. So the 6 centimeter, 18 centimeter is improved to the accuracy. So thank you very much for my presentation. So.
Thank you, Dr. Sasakawa. Yeah. So again, I want to open the floor for any questions. We still have about 8 minutes for this session. I'm not sure online. Can they ask question? No. Okay. So anyone here that would like to ask question? If not, let us thank the 4 speakers, 2 here and 2 online, with applause. Thank you very much. I would like to close the session and pass the floor to the next session, the moderator for next session. Thank you.